All right, welcome back to the eighth lecture. So today we are going to talk about distributed memory programming and an MPI. Okay, so today in particular we talk about different parallel programming models, message passing interface, and also performance evaluation for distributed memory applications. So if you remember, a couple of weeks ago, we talked about Flyn's taxonomy. So we had system machines in which you have a single processing unit which executes a single instruction sequence, and it works on single data items at the same time. So these are like traditional CPUs, and they can be considered as cores in currently available CPUs, right? Then we had SIMD, or single instruction multiple data machines, where you have different processing units, right? And their work is still on a single instruction stream, but they fetch different data elements from this data pool. So you execute a single instruction, but you work with multiple data. So anyone can tell me a piece of hardware that uses this SIMD architecture?
The GPU?
Yes. So in GPUs, we usually have this SIMD thing, right? And then we had this multiple instruction single data, which we are not going to use. And finally, MIMD, or multiple instruction multiple data, where you have different processing units, and each processing unit can execute a different instruction sequence and work with different kind of data. So these kind of systems are multi-core systems and computer clusters and things like that. So if you further extend the Flink's taxonomy, you can also divide these MIMD machines, like multiple instruction, multiple data, into shared memory machines and distributed memory machines. In the shared memory machines, as we talked about many times, so we have different processes, right? Different processors, and they share a global memory space, and they use this global memory space for communication and for collaboration, right? So a typical shared memory hardware is like multi-core CPUs. And on the other hand, in the distributed memory architecture, so we have different processes, right? But they have access to their private memory address. So there is no concept of global memory address, and everything for collaboration and communication should be done explicitly through this network, right? So each process needs to create a message that wants to send to other processes and then send it through something called message passing interface, or MPI. So this is one of the approaches for sending and receiving messages in a distributed memory system. So an example of a distributed memory system is high performance computing environment, like the ones that we talked in the workshop, like Mahdi, Puhti, Lumi. All of these systems are distributed memory machines. So the focus of today's lecture is to show you how we actually program these kind of systems. Okay. All right, so for programming shared memory machines, we talked about different approaches like pthreads in C and std thread library in C++. We also talked about OpenMP, and today we talk about MPI to program these high-performance computing systems. Okay. But before that, let's discuss a little bit about different parallel programming models and see which model actually fits these distributed memory systems. Just a moment. Okay. So typically, we can divide parallel programming models into globally parallel, locally sequential model and globally sequential but locally parallel models. So in the first group, our application is inherently parallel, so your code is executed in parallel in the beginning, and then you continue the execution sequentially in each subtask. So the application performs multiple tasks in parallel with each task running sequentially, right? So we have different models for this GPLS thing, like single program, multiple data, or SPMD, multiple program, multiple data, or MPMD, master worker architecture, and MapReduce architecture. So all of these architectures can be used in distributed memory systems, and they are categorized under this globally parallel, locally sequential category. Okay. So on the other hand, we have this globally sequential but locally parallel models where you start your application sequentially, but then during the execution, you like spawn some threads to have some parallel execution. So your application execute as a sequential program with individual parts, with individual parts that is running in parallel. So this is the typical model in OpenMP, for example, or these pthread and thread library, like this fork join model and loop parallels. So these models, the globally sequential, locally parallel model, is usually they're usually used in shared memory systems, but this globally parallel, locally sequential model is used in distributed memory systems. And today in particular, we're going to focus on this single program, multiple data, which fits quite well into MPI model. And here is an illustration about these two models. So as you can see, in globally parallel, locally sequential, you just need to do some initialization, like in serial, but the whole program is run in parallel here, right? So you cannot really make your code sequential during the execution. So everything is started in parallel. But in globally sequential, locally parallel model, so you can start with a single thread, then you have a parallel execution, then probably you want to have another round of serial execution, then parallel execution and serial. So this is fork join model that we talked about. So in distributed memory machines, we usually have this globally parallel, locally sequential thing. Okay. So as I mentioned, SPMD, or single program, multiple data, is a paradigm or model that we use in distributed memory systems. So, and here how it works on a single machine. So typically you have a source code that you compile and link to create an executable. Then in SPMD, you execute this executable in different OS processes, right? So then each OS process executes your executable, and because it's a process, it has access only to a piece of like private memory. So this executable works on different part of data, right? And this executable in this process works on another portion of data, and finally this one as well, right? So this is how SPMD works on a single machine. You have different processes and they can collaborate with each other through message passing, and then they can provide the result for you. So in this SPMD setup, you usually need to initialize your program. So how many processes and how many threads within the process is needed. Then you need to provide a mechanism for obtaining a unique identifier for the process, because based on this unique identifier, which can be a process ID, for example, you can divide the job or divide the task between different processes. Then you run your program, and finally you need to shut down the program to free up like allocations and threads or processes that you have created. Okay. So as you can see, this is quite important to know that you have a single program. So you have a single executable that is executed by each process, right? But they can work on different data. So that's why it's called single program, multiple data. So it's in the topmost level of parallelism hierarchy. So in the lowest level, you have SIMD, single instruction, multiple data, where you have a single instruction, and that single instruction is working with different data. But here you have the entire program that can work with different data. And this is how you can see it in a single machine. But because here we are working with the concept of processes, so we can also consider multiple machines. So for example, in a computer cluster, as you can see here in this figure, we can have two nodes, right? Each node has a couple of CPUs, right? And each CPU has different cores, as you can see here, right? So it's up to the programmer how you want to dispatch your processes into the CPU. So for example, here I can create a process, and then I can execute that process in a single core, or I can execute that process on a single CPU or a multi-core CPU, or I can execute this process on the whole machine, right? So you can see SPMD can be interpreted in different manners. So from a single computer to a single CPU, or to a complete and full computer cluster. And when you want to execute your SPMD programs on a computer cluster, so you write your code, you compile your code, and then the queuing system, like a Slurm that we talked about before, sends this executable to different nodes, right? And then each node will execute this executable. And you can have different data in each node, right? So in the context of SPMD, a process or a processor can be considered as a core or a multi-core CPU or even a full machine. So this is quite flexible approach when you write parallel applications. So that's why you can write massively parallel applications in computer clusters with hundreds of thousands of nodes and CPU cores. All right, so let's see the other distributed architecture that we are not going to use in this class, but I just wanted to familiarize you with that, which is called MapReduce. So this is also a distributed architecture, but it is not like strictly following SPMD. So here in MapReduce architecture, which is developed by Google and is used in Hadoop and also Spark, you have a huge amount of data that you want to process, right? So you cannot really store data in a single machine. So you have to distribute the data. So you divide the data set between different partitions, like partition 0, partition 1, and so on. And then you create some workers, and these workers can be a node in a cluster. And each worker basically works on the different portion or different partition of the data, right? So if we have 4 partitions, we can have up to 4 workers, and each worker works on its partition, data partition, right? And then they compute some partial results based on the data that they need to work with, right? So first worker works on this data partition and then provides the partial results, and others do the same, right? So this stage of partitioning the data and mapping this partition to a worker is called mapping in MapReduce. So in the mapping stage, you just map the portion of your data to the dedicated worker, and then you compute some results that you want. It can be like a pre-processing result or something like that. And then you combine the the partial results provided by each worker into the final result. And this stage is called reduction. So that's why this architecture is called map reduce. You map in this stage and then you reduce here. So it's the map reduce architecture. It is used a lot in big data and data science when you want to like process a huge amount of data in a distributed system. Okay. So any questions so far? All right. Okay, so now that you know different architectures in distributed memory systems, so it's essential now to talk about message passing because, as I mentioned, in a distributed memory system, you should be able to send messages between different processes because different processes have their private memory. So when they don't have really access to each other's memory and they need to send messages through the network. So for example, in this figure, we have two CPU cores and we have a process in each CPU, and each process has access only to its private memory, right? And in that memory, we have some data. So the idea is to send this data from this core to another core through the network, right? So this is basically called message passing, and you can have these CPU cores available on a single machine, or they can be in different machines. So it really doesn't matter from this abstract point of view. Okay. So typically in a message passing environment, we have P processors, right? And they have access to their private and exclusive memory, right? And all the data that you want to send, they have to be like explicitly partitioned and placed. So everything should be explicit, and you need to know exactly what kind of data, how many bytes, for example, what are the data type you want to send. And in this case, all interactions take place between two processes, right? In most of the cases. So in the lowest level, you need to have at least two cores or two processes for this message passing to happen. So it's a two-sided communication, which is about like that. So you can see it like one process wants to send the data, right? And another process wants to receive the data, which roughly means one process needs to call a send routine or function, and another process needs to call a receive function, right? So everything should be quite explicit. And when you have message passing, you typically use this SPMD model. Okay, so there are a lot of libraries for implementing this message passing. One of them is message passing interface or MPI. So basically, MPI itself is not a library, so it's a specification which defines a set of APIs for message passing, but it can have different implementation. So we have like Open MPI implementation, which is open source, and we have also MPitch implementation, which is also open source. And there are also other implementations provided by like vendors like Microsoft and uh, and Intel as well. But in this class, we use OpenMPI as our MPI implementation. And on Mahdi supercomputer that we talked about, you can also activate this OpenMPI. So the question is how we can activate OpenMPI on Mahdi. So anyone remembers that? We talked about this last week.
I think there was a command with a load.
Yes, module
Yeah, module
load.
module spider for the detail and module load for the
Yes, exactly. Yes. So you need to search for this package using module spider. And then when you find the specific version, you can use module load and that OpenMPI version here to load it into your environment. And then it gives you the utilities that you need to have for compiling your MPI program and for executing your MPI program. Okay. So MPI is actually available in C and Fortran by default. So you have them on C and Fortran, but there are also available Python bindings like to be used in Python. So in Python, you can use this MPI for Pi library, which is a Python binding for, I think, OpenMPI, if I'm not mistaken. And then you can easily install it using this pip install MPI for Pi. And then if you need to see the documentation or tutorials, you can open this link. And it is also available in some other programming languages. For example, you can also find Java MPI bindings. But in this class, we mainly use on the C interface, C implementation, and also C++. There are actually interfaces for C++ as well, but the focus here is to show you how this C interface works. All right. So in MPI, all communication, synchronization, and all of the functionalities that MPI provides for you, they require subroutine calls or function calls. So you have different functions for different MPI feature. And it also provides communication subroutines or communication functions. And you can divide them between two categories. So you can have point-to-point communication routines and collective communication routines. So in point-to-point, you usually have this send and receive, where you want to send some data or you want to receive some data. But in collectives, you have routines for moving data, like a broadcast, gather, and scatter that we are going to talk about today. And sometimes you want some routines to compute and also moving the data. For example, you want to sum some elements of the data and then you want to send it to different processors. So all of these things are supported by MPI and you can use them through MPI subroutine calls. And it also provides some subroutines for synchronization. So for example, you have barrier in the simplest case. Then it can also provide some inquiries, so you can understand, you can like having your program, how many like processes you're using, which process you are, the process name, this kind of information. But the most important part is this communication subroutines, which implements the actual message passing logic. So how you want to send and receive data between like two processes or between many processes. All right, so this is the Hello World application in MPI. So I wrote it in C, but you can also write the same thing in C++. So to start with, you need to install MPI that I'm going to show you in the next slide. After installation, you will have access to this MPI.h header file. So you have to include this, and all of the MPI routines are implemented in this header file. And then I have my main function, and this is my MPI program. So we will talk about this program in details in a minute, but just want to give you some big picture about the basic structure of an MPI program. So every MPI program, or at least the MPI portion of your program, should start with this MPI init and should end with MPI finalize. So if you want to start your MPI program, you have to include this MPI init function. You have to call it, and after you've finished your MPI program, you have to call this MPI finalize. We will talk about these functions. And then what you typically want to do is to get the rank of your process. And the rank of a process is a unique identifier for that process, which is a non-negative integer number. So the rank starts from 0 to, and it's smaller than the size. What is the size? The size that you can get with this command, MPI comp size, is the total number of processes that you're using in your MPI program, right? So you need to get the rank, which is the ID of your processes, and the size, which is the total number of processes that you're using in your MPI program. And you can get the rank with this MPI com rank function and get the size with MPI com size function. And in both functions, you need to pass in this micro, which is called MPI com word, which is a communicator that we're going to talk about. But a communicator basically designates all processes in the MPI job. So all processes that you have in your program are within this communicator. So basically you can see the communicator as an environment where you have different processes, and the processes within this environment can only communicate to each other, right? So if you have two environments or two communicators, then it's not straightforward for the processes in this communicator to communicate with the ones in this communicator. So the communicator includes the processes that can communicate with each other. And the default communicator is this MPI com word communicator, which is created when you call this MPI init function. Okay. So I get the rank, I get the size, and then I can like print which rank I am, like and in which size. Okay. So we should also talk about the execution model of this program, but I will do it in the next slide. All right. So in order to compile and run this code that I showed you, you need to install the MPI implementation. So in order to install OpenMPI implementation, if you're using Ubuntu, you can use this sudo apt install OpenMPI bin and for the binaries and lib OpenMPI dev for the library. If you're using like CSC or these supercomputers, you don't need to install anything. But if you want to use MPI on your like single machine for single program, multiple data model, you should install it with this command. Or if you use Mac OS, you can use it using this homebrew, using homebrew install OpenMPI. All right. So if you install these like OpenMPI successfully, it gives you some utility commands. So the first thing that you need to know is compilers, MPI compilers. So for compiling MPI applications, you cannot really use GCC or G++. You need to use MPI compiler. So in this case, if you install this OpenMPI, you have this MPI CC. If your code is pure C, or MPI C++, if your code is C++, right? And then you can compile it like normal. So you don't have to specify this -G and -vol. Plus G is for the debugging, like information, and vol is for the warning. But you can compile it like a normal C program then. So you write the executable file, and then you provide the source file. And if you're using C++, you should do the same thing. So this is the compilation procedure when you are using the command line interface. But if you use CMake, you can also set up MPI quite easily. So you define the CMake minimum requirement, and then the project name and the language. Then you use this find package, which allows CMake to find MPI if it is installed on your machine. Then you include the MPI directories, like the header files. Then you add your executable, and then you link MPI libraries. So quite simple. Okay, but how we can execute an MPI application? So if you just run this hello.mpi, so assume I compiled my program into this hello underline MPI. So if I run it as a single executable, then my operating system creates only one process for this application, right? So in this case, it's not going to be an SPMD. So it's a single process application. So in that case, my rank would be 0 and my size would be 1, because I only have one process in the communicator. So in order to run your application with multiple processes, you should use MPI run or MPI exec, and then you specify the number of processes, right? With -np, number of processes, then the number of processes here. And then you specify the executable name. So in this case, this MPI run launches 4 processes, and each process will run this hello MPI executable. And in this case, if you run it in 4 processes, so this code is executed by each process at the same time, roughly. So in that case, the size will be 4, and the process 0 initializes the rank variable to be 0. Process 1, in that case, the rank will be 1. Process 2, the rank will be 2. So you can see this program to be executed on different machines, and then in different machines you can have different ranks. Okay. Or if you're using a computer cluster or a Slurm, so instead of this MPI run, you can use this srun if you're using a Slurm. So I will show you an example like later today, but it's important to know that when you compile your program, you will get an executable. And then when you use this MPI run, this executable is executed within different processes, right? So if I have 2 processes, I have this hello MPI in one process and hello MPI in another process. And they both execute the code in this process, in this manner, okay? So any questions about this single program, multiple data execution? All right. So now let's talk in detail about different MPI components. So the first one that we talk about is this MPI init. So as I mentioned, every MPI program needs to start with this MPI init function. So what it does is to set up some memory allocations, some processes, some threads in MPI. So you have to call it first for these initial allocations and necessary setups. And then when your MPI application, your MPI program is done and you want to like close your program, you have to use this MPI finalize function. And this MPI finalize function basically deallocates all of the memories that were allocated by the MPI itself, not by you. So you are responsible to free up your own memory allocations, and this MPI finalize is going to be responsible to free up the memory allocations done by the MPI itself. So for example, in the simplest case, when you have an MPI application, you call this MPI init, then you write your MPI code here, and after your MPI code is finished, you just call MPI finalize to free up everything. So this is the very basic structure of an MPI program. And the next concept that you need to know about an MPI program is the concept of a communicator. So a communicator is a collection of processes that can send messages to each other. So basically they can communicate to each other. So when you call this MPI init, by default, it defines a communicator, and that default communicator consists of all processes that you created for your program, right? So this default communicator has all of the processes that you want to use in your program, and it is called MPI convert. So this MPI convert is the default communicator. You can also create your own communicator as well. So when you have a communicator, you can get the number of processes within this communicator using MPI com size, and you can get the rank or the ID of the calling process in the communicator with this MPI com rank, right? So in both functions, you need to specify a pointer to an integer and also this communicator as well. All right. So let's see how we can send and receive messages in a communicator. So for sending a message in MPI, you have this MPI send routine. And for receiving a message, you have MPI receive routine. So in the MPI send, you have to provide all of these parameters. So you have to provide a pointer to your data that you want to send. And it can be a pointer to anything. Then you need to specify the size of your message. So how many elements you want to send. Then you have to provide MPI data type. What is the data type that you want to send? Is it a double? Is it an integer? And you should define it using MPI data type. So MPI only supports some data types that you can send. So your data type should be supported by MPI. Then you provide the rank. This is the rank. Then you provide the rank of the destination process. So which process you are sending the data to. Then you can define a tag for your data. So you can tag your data for the receiver to identify which data exactly it needs to send to receive, and then you provide the communicator. So this MPI send, and which tells you which communicator is responsible for this MPI send operation. And in MPI receive, you again need to provide a buffer or a message buffer, which is a pointer to anything, but basically your data. Then the buffer size, the data type, the source. So which process this process is getting data from or receiving data from. Then which tag you want to use for receiving data. So basically using this tag parameter, you can filter the data that you're receiving. Then you specify the communicator and then something called MPI status, which gives you some status about the send and the receive operation. So here I want to show you a code snippet that we have different processes. So in this case, we have 4 processes. So this is the process 0, which is the rank, process 1, process 2, and process 3. And we want process 1, 2, and 3 to send some data to process 0, which is called a root process. So process 0 is called a root process. So I repeat again. So process 1, 2, and 3 want to send some data to process 0, and process 0 wants to receive data from these processes. So let's see how we can code this example. So first, I need to include MPI header file, and then a standard C headers, and then I define a maximum size for my data, which is in this case a string. Then I write rank and size. So I initialize this rank and size variables to get information about the rank of the process and the size of the communicator. Then I define a buffer for my message, which is an array of character. Then I define a status for my MPI, so which is this variable. Then I should use MPI init, write my program, and MPI finalize. Okay. So this snippet here implements the send and receive logic. So since this is an SPND program and it is executed by all processes, so I can use this rank variable to make decisions. So in this case, I say if the rank is not 0, so if rank is either 1, 2, or 3, right? I create this message, which is the hello from process and rank. So I create a message if I'm not rank 0, so if I'm not the root node. And then I call MPI send, right? So I send a message, and this is the size of the message. I use MPI char. I send it to node 0, right? And we tag 0. So I tag the message 0, and then I provide this MPI convert, the communicator. Then if I am if I am the root node, so I execute this part. So this portion is executed by process 1, 2, and 3, but not 0. But this portion is executed only by process 0, only by the root node. And in this case, I loop through all process IDs, right, from 1 to size, and then I call this MPI receive routine. So I receive message, right? With this size, and it is a MPI char. So I get it from the source. Source is 1, 2, and 3. The tag is 0. I provide MPI convert, the communicator, and the status. And then I call MPI finalize. Okay. So if I am the root node, I call the receive function with different sources. And if I'm not the root node for this master worker architecture, if I'm not the root node, I send some data, I create and some data, right? And you can think, if you think about it, you can see that like all of these processes, they can live in different machines. So if I want to run it on a supercomputer, in this case, I have 4 nodes, and each node, and I have a root node which receives the data, and I have worker nodes which send the data. So let me show you the actual implementation and how you can compile such a program. So I wrote it a little bit differently. So here in this slide, I showed you how to send a string, but in the code, I'm going to show you how you can send an array of integers, for example. All right, so let me share my VS Code. Okay, can you see my VS Code window?
Yes.
Okay, so here I have 2 files, main.cpp, which implements my MPI program, and also CMake file. So in the CMake file, I provide the CMake version, then the languages and my project name, C++ standard, and then I use this MPI find package MPI to find the MPI package. Then I just do some checks. Then I include the header file, add executable, and I link the shared libraries of MPI. So it's easy for CMake compilation. All right, and this is my program. So I include MPI header file, right? I call this MPI init function to initialize MPI. Then I declare this rank and size variable. I get them using MPI com rank and MPI com size. Then I allocate actually some memory to have my data. So in this case, I got some memory for 5 integers. Then if I'm not in the root node, so I'm a worker node, I initialize this data with my rank. So just a number that is like dependent on the process. And then I call this MPI send to send this data, which is initialized now, to node 0, to the root node. And then I print some information that I just sent the data and I show the data, right? And if I was the root node, so I look through the indices of the processes, then I call this MPI receive function. So in the first iteration, I receive data from the first process, and in the second iteration, the second, and so on. Then I print the data that I received from the processes. Then I deallocate the memory that I allocated and call this MPI finalize. So let me compile the code without CMake. So with CMake it's quite simple, but I do it without CMake here. So since it's a C++ program, I call this MPI CPP. So this is my compiler. Then I provide the name of my program and then the executable, right? So let me run the application now. So you can see I have this app executable here. So let me run it like a normal program. And let's see what happens. So if you can see, nothing is printed out to the screen, right? So take some time and let me just maximize the window. Okay. So take a minute and tell me why, if I run my application as a like normal program, not an MPI program, nothing actually prints out to my console. What's happening here? Can someone tell me? Let me just show you the code. All right. So you have about 1 minute or something. All right. Anyone has an idea?
I think maybe the ranking doesn't work and only the root node tries to receive, but as nothing is sent, it receives nothing.
Okay. So any other answer? Okay. So let me now let's think about it together. So when I execute this program, like as a normal program, not an MPI program, what would be the value of size and rank in this case?
Zero,
So the rank is 0. What would be the size?
1.
Okay. So the value of size is 1, right?
Okay.
So now in this loop, the size is 1, right? Do we go through this for loop now if size is 1?
No.
So that's why we don't print anything, right? So
Yeah.
because the size is 1, because we only have one process here, and rank 0 wants to get data from other processes than rank 0, right? So we don't go through this loop and nothing is received. So now let's execute it as an MPI program. So I use this MPI run -n or np with 4 nodes and my application. So now let's see what is printed out. So we see that rank 2 sends this data, right? 20, 21, 22, 23, 24. Rank 1 also sends this data. Rank 3 sends some data, right? And then we have received this data by rank 0. So rank 0 received data from rank 1, and this is the data which matches with this rank 1. Rank 0 received data from rank 2, right? Which matches the rank 2 data. And finally, rank 3. So now let me run it with, let's say, 11 processes. Then I get the same thing, right? But with more processes. But what if I use more than 11 on my particular system, like 12? I will get an error. And why is that? Because MPI works quite well with the number of physical cores available on your machine. So you cannot really use an arbitrary number of processes here. I cannot really use 500, for example. I get an error. There are some techniques to work around it, but you it's not efficient and you lose some performance. So always when you use MPI, try to use the number of physical cores that you have available, right? Or the physical cores that you allocated on a supercomputer. So in my system, I have 11 physical cores, then I can use up to 11 processes. So from one process to 11, 2, then 3, and so on. Okay. All right. Any question about this program? All right. So let's share the slide again. Okay. Can you see the slides?
Yes.
Okay. So this is how you use this send and receive thing. And about the MPI primitive data types, you can use different data types like MPI short, MPI int, long, and so on. The most popular ones are MPI int, float, double, long double in some cases, MPI char for character or strings, and things like that. Okay, there are some important things about this send and receive APIs that MPI provides. So typically, when you use MPI send, according to the documentation, the calling process may block until the message is received by the destination process. So if you run an MPI send, right, and there is no MPI receive, you probably get blocked. Your process may block, right? Or if you like do not call MPI send or just MPI receive, if you call only MPI receive without any sending, again, the process that calls this MPI receive will block. So these are blocking operations. MPI also provides non-blocking operations that we are not going to talk about. So the most important thing about this MPI send and receive is that they are blocking operations. So now, taking into account that API send and MPI receive may block, so someone tells me what is happening in this code here. Does it execute normally or something strange happens? And what, if happens, what is that strange thing? So take your time, about a minute, and think about it. Okay, I'm not sure if it was a minute, but anyone has any ideas what's happening here?
I think because of the reverse order of sending and receiving,
Mhm.
the program is going to be blocked and not move forward from the send A because the other the other node is looking for message B, but
Yes,
it
that,
hasn't
that
received yet.
Yeah, that's exactly true. So if your rank is 0, so the process 0 sends some data to process 1, right? The first data is sent with tag 1, and the second one is sent with tag 2. And for other ranks, if you are rank 1, you're looking for the data, right, with tag 2 from node 0. But the data tag 2 is received when the first one is sent, according to this here, this line here, right? So then this line blocks the program, and also this one. So you get a deadlock here in this case because you're waiting for the data that is not sent, right? All right. So deadlocks can really happen when you work with MPI, and in some scenarios they are quite difficult to catch. So you really need to know what you're actually doing, and try to avoid actually deadlocks because they are quite resource intensive, and your program might be locked forever. And it becomes even more important when you use these computer clusters because they have some functionalities that stop your execution. You will know it like later after you waited for a long time in the queue. So try to test your programs to avoid deadlocks before running them on the computer cluster. All right. So these were point-to-point communications in MPI. So MPI also provides collective communications, which are quite important. In practice, it is quite rare that you use point-to-point communications. And typically, what you want to do is to use collective communications, right? So in collective communications, the communication operation usually is defined over all processes within a communicator. So all processes in a communicator, they must participate in the operation, and they have to call the same routine for that communication. So for example, if you want to broadcast data from one node to another, all of the nodes, even the node that is broadcasting, should call the broadcast routine. So we'll talk about that. In the simplest collective operation provided by MPI is barrier synchronization, which is used when you want all processes to wait until all others reach that point. So if one process calls this MPI barrier, then it needs to wait for the other processes in the communicator to call the MPI barrier. Then after all of them call this MPI barrier, they can move forward with the execution. So we talk about barriers a little bit in this lecture if we have time. Okay, so the first collective operation that I'm going to show you is all-to-one reduction or reduce. So in this case, as you can see here in the figure, let me first explain the figure a little bit. So in this figure, the vertical axis shows the processes and the horizontal axis shows the data, right? So if you have different data elements in processes, so A0 is in the first process, A1 is in the second process, and so on. When you apply reduction, all of these different data elements that are stored in different nodes are combined, right? They're combined. For example, we can sum them up, we can multiply them, and then stored in one of the processes. So this is called all-to-one reduction, right? So assume we have different numbers stored in different machines, and then we want to sum them up and store them in the first process. Then we can use the reduction. So this is from data flow perspective and from the network perspective. So here, assume we have 4 processes with rank 0, 1, 2, and 3. And each process has some data. So rank 1 stores like number 2, rank 2 stores number 3, and rank 3 stores number 4. So with the reduction, we just combine these values, right? Sum them up and send it to the root node in this case. So the root node receives the reduction, the result of the reduction operation applied to these 3 processes, right? So how you can do a reduction in MPI, you should use this MPI reduce function. And this MPI reduce function is called by all ranks, right? Not only the senders. So you should provide the data using a send buffer. Then you should provide a receive buffer for receiving the data, the number of elements, the data type, the MPI operation. For example, in reduction, you can have MPI sum, MPI like multiplication, and things like that. So the operation that you want to use in the reduction. And then the target node or the target process. And then you specify the communicator. So let's see an example. So again, I start with MPI init and I finish with MPI finalize here. I get the rank and size using these 2 routines, right? And the value that I want to apply the reduction is the rank itself. So I want to sum the value of the ranks. So this is the data that I want to apply the reduction, and this is the result. So just some memory for the result. And then I call this MPI reduce. So the send value, the data, the result, right? So it is one integer. I want to apply MPI sum, and I want to have the reduction result on node 0. And then I provide this MPI communicator. Again, note that this code is executed by all processes at the same time. So all processes are calling this MPI reduce function. Here we don't have if statements for branching, because in collective operations, all processes need to call the collective operation. And then if I execute it, I will have the sum of the ranks in the node 0. Quite simple. All right, let's talk a little bit about the implementation, because like internally MPI uses a tree structure. It can be different tree. It can be a binomial tree. It can be a binary tree to perform this computation. So for example, in this case, we have 7 processes, right? So process 1 sends its data to process 0, 3 sends to 2, 5 sends to 4, 7 sends it to 6, right? So in our example, so 2 from 1 is sent to node 0, and then node 0 applies the sum and obtains 7 and stores 7 in node 0. Here, node 3 sends -3 to node 2. Then we apply the sum in node 2 and we get -4. And this is stored in the node 2, and 7 is stored in node 0. And then node 5 sends its value to node 4, and node 4 sums them up. So sum 6 and 5, so it gets 11, and 11 is stored in node 4. Node 7 also sends 2 to node 6, and node 6 sums -7 and 2, and gets -5. Okay, so now in node 0, node 2, node 4, and node 6, we have some intermediate results. And we do the same thing again. So now node 2 sends the data to node 0, -4 is sent to node 0. Then we sum it with 7, and we get 3 in node 0, right? And then here, node 6 sends the data to node 4, and we sum it here, and we get 6 stored on the node 4, right? And then in the last step, node 4 sends 6 to node 0. And node 0 sums it with 3 that was there before, and it gets 9. And this is a tree structure for doing this reduction, right? You can do it linearly, but for efficiency, we use a tree. So someone can tell me what is the computational complexity of this tree? Any ideas? It is O of what?
Logarithm of n.
Yes, and n is the number of processes, right?
Yes.
So this is typically how MPI implements these like MPI reduce operation and others as well. So it creates a tree, and then so it creates a tree of processes, and then it sends the data on the tree. And this is another structure for the tree. So I try to explain it quickly. So you divide the processes in 2 groups. So the second group, like here, sends the data to the first group. So 4 sends it to 0, 5 sends it to 1, 6 sends it to 2, and 7 sends it to 3. You do the summation here, and then you again group them into 2 processes. So in this case, 2 sends it to 0, and 3 sends it to 1. So you get here, you then group them again, and then you send 1 sends to 0, and then you get the final value. So it really depends on the structure of the tree and implementation details. When you work with MPI, you really don't need to worry about these algorithms behind the scenes, but you should really know how to work with the API, like this MPI reduce function. All right, and this table shows you the predefined reduction operations, so you can get the maximum, minimum, sum, product, and some others. All right, so the next operation is all-to-all reduction, which is also called all-reduce operation. And it has a lot of applications in distributed machine learning and distributed data parallel training, because you want to usually perform this all-reduce operation. And I will show you how it actually works. So like before, we have different pieces of data stored in different nodes, right? We try to sum them together in case of the sum. And then instead of sending the reduction result only to node 0, we send it to all nodes in the communicator. So after the all reduced reduction, all of the processes will have the result of the computation. In machine learning, for example, you want to compute the gradients of the loss function locally, right? And then you want to take an average of the gradient and make it available for all other nodes. So that's a quite typical and common operation in distributed machine learning, and that's why this all reduce operation is used a lot in distributed learning. Okay, so the MPI routine that implements this all reduce is called MPI all reduce. There should be an R here, all reduce. So you need to provide the send buffer, the receive buffer, number of elements, the data type, so these are common, and the operation. you want to do a sum or product or something, and then the communicator. So in this case, you don't really need to specify the destination rank because all processes will get this data. And here is an example. So you start with MPI init, you get the rank, size using this, right? So this is my value that I want to send. This is the result. And then I call this MPI all reduce. Quite simple. And here is the internal implementation. So I just briefly explain it. So what you need to do is to do the reduction as before. So this is the exact same tree that I showed you before. You get the result, and then you traverse the tree in a reverse order, and you send the data back. So for example, 9 gets data from, node 0 gets data from 1, from 2, and here from 4. So it sends back the result to 1, to 2, and to 4. So it broadcasts the results to the nodes, and then other nodes, they do the same thing. Okay. So the next operation is broadcast or one-to-all broadcast. So it's quite simple operation. So assume you have some data in node 0 and you want to send it to all other nodes. So this data after the broadcast operation will be available in all processes within the communicator, right? So here you can see the communication. So you have this data here, and after the broadcast, you have it in the node that had it before, and also other nodes. So the MPI routine for that broadcast is MPI bcast. Again, you need to provide the buffer, the number of elements, the data type, and the source, which is the process that is sending or broadcasting the data, and also the communicator. That's also quite simple. So in this case, so these parts are common. So you get the rank and size, and then if the rank was 0, you produce some data here, and then you call MPI broadcast. And then all other processes will have this value 42 that was only defined on node 0. Okay. And for the internal implementation, MPI uses the same tree that I showed you in the all reduced operation. Okay. The next operation is gather and scatter. So these are quite important. So in the scatter operation, you have different kind of data on a node, right? So here we have these data elements A0 to A5 stored on node 0. And after the scatter operation, each part of this data is stored on different nodes. So A0 stays in node 0, A1 goes to node 1, A2 goes to node 3, and so on. So this is the scatter operation. And the reverse operation of a scatter is called gather. So in gather operation, you have different data stored in different nodes, but you want to stack them. This is not a reduction, so it's important to know. You want to stack these different data points or the data elements in one node. So this is called the gather operation. So here I'm showing the scatter. So we have different data elements stored in node 0. And after a scatter, each portion of data is stored in different process. So this is called MPI scatter. And for using that, you should provide the send buffer, the number of elements, the data type, the receive buffer, the number of receive elements, and the receive data type, the source where you want to send the data, and also the communicator. And here is a small example. So this is my data stored on my node, right? And then I call the MPI scatter, right? So it sends different parts to different nodes. Okay. And as I said, the MPI gather is the reverse operation of MPI scatter. So you have different portion of your data in different nodes, and then you stack them in MPI gather. So this paradigm can be used for implementing a distributed array where you have different portion of this array stored in different nodes. And for the gather, you can use MPI gather, which is quite similar to MPI scatter. So you have to provide the send buffer, the number of points, data type, receive buffer, and the target where you want this data to be gathered. Okay? And this is not a scatter gather. All right. And here is a small example. So you have like different data in different nodes, and then you use MPI gather to stack them in one of the nodes. And in this case, we use node 0. And finally, we have the all gather collective operation, which is quite simple but expensive. So in all gather, instead of stacking the data in one node, you stack the data in all other nodes as well, right? So this is called all gather. So in this case, in the right, we have 3 data elements, right? So we stack them up, but instead of sending them only to the target process 0, we broadcast it to all other processes. So after all gather operation, you have the stack data stored in all the processes. And in MPI, you can use MPI all gather. And again, you need to provide the send buffer, the number of data types, and the receive buffer, and the number of data, and also data type. And then finally, the communicator. And this is a very simple code snippet that you can see how this MPI all gather actually works. Okay. So we covered point-to-point operations, send and receive, and also collective operations like broadcast, reduce, reduce, gather, scatter, and all gather. And the final topic for today is to show you how you can like evaluate the performance of your MPI implementations. So we talked about performance evaluation a lot a couple of weeks ago, and today I'm going to show you briefly how you can apply those techniques into MPI applications. So for an MPI application, you can use MPI W time to measure the wall clock time. If you remember in OpenMP, we had something similar. So in MPI, you should use MPI wall clock time, right? So you can use it that way. So you call it before the code snippet that you want to measure, and also you call it after your code snippet, and then you can compute the elapsed time. But in MPI, as I mentioned, this code will run on different processes. So which means you can have different different time measurements. So in order to make it more accurate, you should call this MPI barrier before measuring the time. So to make sure that all processes reach this point together, this point together, right? And then you compute the time, the elapsed time, right? And then using MPI reduce, you compute the maximum time, provided by the slowest process, and then you report the maximum time. So this is typically how you can get the execution time in an MPI program. So you want to know the time taken by the slowest process. And after you have this wall clock time, you can compute the speed up, the efficiency, the strong scalability, and also weak scalability, and you can come up with the efficiency graphs that we talked in the performance evaluation lecture. Okay. So this is basically what I wanted to cover for today, to show you what is MPI and how it works. And in the next lecture, which would be the last one, we're going to talk about some real world MPI examples and applications. I tried to provide a simple distributed machine learning example and show you how you can implement and how you can design and implement a distributed machine learning algorithm from scratch using MPI and execute it on Mahdi supercomputer. All right. So is there any question?
Will you upload the Mahdi workshop on Moodle?
Yes, I had some problems with with editing the video. So because there are some changes that I need to do. So I try to upload it today, at most tomorrow. So, but I'm not going to upload it on Panopto, so it's going to be uploaded on YouTube, so you can watch it there.
Okay.
Right. Any other questions? All right. So thank you for your presence, and have a good week. See you next time.
You too, Brian.
Bye.